There are three types of radiation that you guys need to know about, and they are alpha, beta, and gamma. All right, so alpha, often abbreviated with the Greek letter alpha, beta, the symbol looks like that, and gamma, which looks like a weird, there you go, kind of a Y thing there. Right? Now, the idea is that you want to be able to compare these in all sorts of ways. So one of them you want to be able to talk about is what is their ionizing power? Should give myself a little more space than I didn't. All right, alpha down here. So alpha actually has a very high ionizing power, which means that it will ionize. Remember, ionize simply means to charge, right? To take away or give electrons. Almost any particle it runs into. So it has a very strong ionizing power. Beta has a very it's middle. You'll find that for a lot of these, it's kind of in between these two. So I'm going to put medium, and gamma has a very weak. But because of these ionizing powers, that's one of the reasons that the penetrating power, which means how far does this radiation travel, these are basically inversely related. So alpha, because it ionizes almost everything it encounters, it then doesn't travel very far. So this is very weak. And because gamma has a weak ionizing power, it's virtually infinite. So it's very strong. And beta is still medium. All right. So the ionizing and the penetrating power are inversely related. This one ionizes almost everything, which means it doesn't go very far. Okay. So if you want to think about, well, how far does that actually go? What does that mean? You're talking a matter of no more than 10 centimeters for alpha. Okay. Beta, depending on how strong the source is and things like that, anywhere from 5 to 10 meters maybe. And gamma they're virtually infinite, right? Think about, I mean, they're part of the EM spectrum, so they'll travel forever in a vacuum, and they are small enough that they can get through almost anything. So what do you stop them by? So the shield are, how do I say it? Stopped by. I don't have a brilliant way of phrasing that, guys. But all right, so if you want to stop alpha, you can simply use paper. Just a sheet of paper will be enough to stop the alpha because it will ionize everything within the paper and then it's done. Okay, beta, usually what we use is a thin aluminum sheet, okay, or glass could also work. Or I'm sorry, aluminium for those of you that are British. All right, and then this needs to be lead, and it needs to be thick. A thin layer of lead will not cut it. And if you think about, we also use lots and lots of concrete, which isn't very reasonable if you want to stop gamma reaching your body, but that's what we use in like the nuclear reactors. Okay, so yes, so thick lead shielding, aluminium or aluminum, or some paper is going to stop the alpha. Right now, these are your three types of radiation, but what does that mean? Okay, the idea is that when we talk about each of these radiations, so what is radiation? Let's start there. Perhaps I should have started there. Radiation is simply the decay of unstable nuclei. And so unstable nuclei come about when you have different, so we talk about radioactive isotopes. All right. And so an isotope is okay, let me start. Okay, all chemical elements are defined by their atomic number. Okay, so let's say, for example, okay, we're talking about carbon. This is a normal carbon atom. Excuse me. All right, so the atomic number, this is the atomic number. All right, and this is the mass number. The atomic number is equal to the number of protons. Okay, this defines what element you are looking at. The mass number is the number of protons plus the number of neutrons. All right. And so if you change the number of protons in an element, you change the element itself. And we'll get to that in a second when we talk about alpha decay. But if you want, but you can have, for example, you could have a carbon. It's called carbon 14 on originally. All right. So for example, now you still have 6 protons, but now you have protons and neutrons add up to 14, which means if you have 6 protons, you must have 8 neutrons. So this would be considered a radioactive isotope. So an isotope in general is an element with the same number of protons, but a different number of neutrons. Okay, so that's your definition for anybody who's concerned. And so the idea is that here, so you have 8 neutrons. Now, that means that this isotope of carbon is actually a bit unstable. And so at some point, it will undergo radioactive decay. All right, and the radioactive decay for carbon, anyway, is, sorry, that's not important. So the idea is that you're going to lose, and so when this nuclei decays, then you can have 3 different types, and that's the alpha, the beta, and the gamma. Okay, so if something undergoes gamma decay, then it's not actually changing any part of it. But if it undergoes alpha or beta, it does. So let's talk about that. All right, so let's look at an example of alpha decay, for example, first. So alpha decay. So let's take a radium atom. All right, so this is a radioactive isotope of radium. And this type usually undergoes alpha decay. So an alpha particle is the equivalent of a helium nucleus. All right, let me go back to my, here we go. Where shall I put this? So here, in between here, sorry for the mess, guys, but the particle itself, all right, this, you can either call it an alpha particle, or you can literally write a helium because that's the same thing. All right, but this is the atomic number, if you will, and the mass number, that's a 2, of an alpha particle. All right, and just for reference, for example, for a beta, when a beta undergoes decay, you guys are only talking about a beta minus decay. That's the only one you guys ever talk about in iGCSE. It's actually an electron. So it looks like this. That's what a beta particle is. All right. And then of course a gamma, there is no particle released, right? It's a wave. So you would just literally just have the symbol. All right. But that's the idea. And again, you could write this if you wanted as a simple beta. Sorry for the confusion. When I talk about this, hopefully it will become clear. Okay. So if this decay, if you're undergoing alpha decay here, right? The first thing that's going to happen is, so the alpha particle itself, so you can put He or alpha, but I'm going to put alpha just to make it clear what we're doing. This is what an alpha particle is, always, 4 and 2. All right. And the idea is that this side of the equation still has to add up to this side of the equation. All right. At least in this type of decay. So the idea is that you have your alpha, and then you're going to have to subtract each of these numbers. So 222 minus 14 ends up being 218, and 88 minus 2 is 86. Now, you don't have to have the periodic table memorized, okay? This is obviously going to be a different element. Remember that this tells you the atomic number defines the element itself. So they will either give you the symbol here and ask you to come up with a number, or they will give you the part of the periodic table that's relevant. You don't have to have that memorized. But just so you know, this is actually radon. And so the abbreviation is RN. It's a radon atom. So now you have, so the radium decays and it releases an alpha particle plus radon. Okay, now what about a beta decay? So let's look at an example of that. So I'm going to take my carbon. All right, so this is my radioactive unstable isotope of carbon, right? And I'm going to put the beta over here this time. So the beta, you have a 0 and a -1. That's all it is you're basically releasing an electron. So here you can also have 0 and -1e. It doesn't matter. Just like, sorry, for this, you can have this, or you can write 4-2he. These are exactly the same when we're talking about radiation, so it doesn't matter. Okay, either one of those. Anyway, so here it doesn't matter. I like the beta because it to me it's clear which one you're actually what you're actually talking about, right? Now, again, the numbers have to add up. So I have 14 and a 0, so it's still going to be 14 here, all right? But now I have to add these up. So I have 6 over here. -1 plus what equals 6? It has to be a 7. So that is going to be the element nitrogen. Again, you don't need to know that. It's just a nitrogen. So this is the idea, right? 7 plus the -1 equals 6. So you have to make sure that your numbers always add up for these types of decay for either alpha or beta. All right, so those are your types of decay. Those are the particles that are involved and the different ionizing and penetrating powers of each of them.